SQL Server 2008 Physical Concepts and Architecture. In this nugget, we're going to talk about the way that SQL Server actually sits on the server and operates. We'll talk about its instances and how those use the various resources of the server, CPU, memory, disk, and so forth. We'll talk about the different services that comprise a SQL Server 2008 installation and cover some of the best practices for assigning those things accounts, which ones to use, when to use them, how to configure them, and so forth. We'll look at the database's physical architecture, how the database is actually spread across the storage system that's storing it on disk, and we'll look at some file placement strategies, both for things like performance as well as for things like redundancy. So let's start with instances. Now, when you look at a SQL Server machine, the actual physical computer, that's not what SQL Server refers to as a server. It's kind of complicated, but the basic deal is that SQL Server itself, its engine, is capable of running multiple times on a single physical computer. So let's just draw some boxes that will represent these instances. Each instance has a name, say A and B, except for the default instance, which does not have a name at all. Here's how those work. If I'm out here on the network, and I try to connect to, let's call it server 1, and I don't specify anything other than the server name, what I will be connecting to is the default SQL Server instance. Now that instance of SQL Server can actually have multiple databases. Each database will have multiple tables and so forth, just like we talked about in the previous nugget. However, if I specify the server name and then a backslash, and then an instance name, then I'm actually not connecting to the default instance of SQL Server. I'm connecting to that specific instance, which has its own databases. Now, why would you have all these different copies of SQL Server running on the same computer? Well, while most of SQL Server's configuration is done on a per database level, there are certain server-wide configurations. For example, there's a server-wide administrator who can control all of the databases on that particular instance. So if I need to separate that security boundary, in other words, if I've got a couple databases that I want Bob to be the super administrator for, but I don't want Bob to have any access whatsoever to this other database, then the only way to do that is to have that on a separate instance of SQL Server. Now, there are other configuration options, and they're all things we're going to look at later when we start installing and configuring SQL, but basically the deal is one reason to have multiple instances is because you need these separate instances to have different server-wide configurations. Now, another reason is for stability. Let's say that Bob over here is doing some kind of funky stuff with his databases, and they're going to be running up a lot of CPU utilization. Well, I can constrain his instance of SQL Server to not be able to use all of the physical machine's resources. I might say that, okay, Bob, you're only allowed to use one of the CPUs, and I'm going to limit you to 2 gigabytes of real memory. That leaves a little bit left over for the other instances running on the computer. Now, what if Bob does something crazy and manages to crash his instance of SQL Server? Well, the other instances keep running, and they're still able to be used. Provided the physical machine is still up and running, those other instances are completely separated from the one that Bob took out. Now, that's great, and it's especially great for hosting situations where you've got multiple customers who are trying to store databases on a single physical machine that they all share. By assigning them each a separate instance, they can be masters of their own destiny, have full control over all of their configuration, full control over all of their security, and if they do something to impact performance, they're primarily only impacting it for their instance. However, there are some resource contentions. There's a reason why you might not want to give every single database its own instance. You've got really just a few basic categories of resources on a physical server. You've got CPU, you've got memory, you got disk, and you got network. Every instance of SQL Server that's running on a computer is going to compete in some fashion for these resources. Now, you might think, well, disk at least is fairly easy to deal with. I can just have more storage, or I can have bigger disks. Well, it's not just the physical storage platters we're concerned with. It's the actual storage, plus it's the storage controllers. In other words, you've got a SCSI interface or something else that's actually getting data out of memory and putting it onto those physical platters. And that can become a bottleneck. If you've got a machine with 2 or 3 instances of SQL, well, depending on what they're doing, you might not notice. If you've got a machine that's running 50 instances of SQL Server, well, I don't care how big the machine is, you're going to run into some resource contention. So you can do things like allocate only a certain amount of memory to an instance. Or you can say that an instance is only going to be able to run on specific processors. And that way you can kind of manually distribute things across those instances. But you always do have to worry. Typically you don't have a ton of disk controllers in a machine. So that's something you may need to think about. And typically you only have a limited number of network connections in a machine. And so that's something you need to think about as you're planning your instances. There's another reason to use multiple instances too, and that's for SQL Server failover clustering. Let's draw a box that represents server 1 and draw another box that represents server 2. Now, let's say both of these guys are running Windows clustering services, which means somewhere behind the scenes they have got one or more shared disk subsystems. These may be connected to the machines by a storage area network, or they may be connected by SCSI cables. It doesn't matter. The point is that both machines are capable of seeing the same disk space. So let's say that on that disk space we've got a database, which we'll label A, and we've got another database that we'll label B. On those servers, we have an instance of SQL Server. Server 1 is running an instance called A, and Server 2 is running an instance called B. Server A is only seeing the data on database A, and Server 2 is only seeing the data on database B. Now, this is kind of an oversimplification of how this all gets set up and works, but the reason it's important to have these on separate instances is so that if Server 1 crashes for some reason, loses power, has some sort of operating system failure, whatever, well, then Server A or Instance A of SQL Server is gone. The trick is you also have Instance A installed but not running on Server 2. When Server 1 stops responding, SQL Server Instance A starts up on Server 2 and connects to its data. Now there's some mumbo-jumbo going on in the background so that when incoming network clients try to connect, they're automatically connecting to Server 1 or Server 2, whichever one has the instance that they're after. And that's something that the Windows Cluster Service actually takes care of for you. So again, another reason to have these instances is because that's part of the strategy for SQL Server failover clustering. Now, another thing you have to take into consideration when you're putting together your SQL Server strategy is services. There are certain SQL Server services that are machine-wide, meaning you only have one copy of those services, no matter how many instances of SQL Server are actually running on that machine. Other SQL Server services are per instance, which means if you've got 2 instances of SQL Server, you'll actually have 2 copies of these services. So let's talk about the instance-specific ones first. You've got the SQL Server database engine, which is the actual, that's what we think of when we talk about SQL Server. So you've got the database engine, you've got the SQL Server agent, which handles a lot of management tasks, things like scheduled tasks within SQL Server, alerting people, alerting operators when there's a problem, as well as handling things like replication and certain other tasks. You've also got analysis services and reporting services. Each instance of SQL Server can have all of these running on its own. Now, you've also got some other that are more machine-wide. You'll only usually have one copy of these. And that includes things like the full-text searching daemon, which handles any full-text searching that you may set up, as well as SQL Server's browser service. And depending on how you set up your computer, you may also have something called integration services. Now, Microsoft has a few recommendations for these. Typically, for the best security, every single one of these is going to be running under a different domain user account. Because each one of these has got very specific security requirements. You're not just going to run them all under local system, although in a lab environment you might choose to do that just for simplicity. In a production environment, though, you're typically going to assign a different account to them. Now, if you've got multiple instances, all of your SQL Server agents, for example, might run under a single account. You don't necessarily need a separate user account for every single instance of SQL agent. It's just all the SQL agents are going to run probably under one account. Again, it depends a lot on what you're trying to do. Microsoft has got some guidance, and I'm going to put a URL up here for you. Go to msdn.microsoft.com /EN-US/library/cc281953.aspx. Not too bad of a URL to remember. And the reason I'm sending you there is because Microsoft periodically updates this set of guidance, these best practices. And this is going to help you figure out what services you need to run, depending on what services you're going to provide to your user community, and how to properly secure those services for a lot of different environments, not just a single domain environment too. So that's all good stuff to know. The main thing to remember for now is that you've got multiple services, some of which are per instance, so we're going to call those instance services. And then you've got other services that we'll call machine services, where really one copy of the service is capable of dealing with the entire computer, no matter how many instances you've got running on that particular machine. All right, in the previous nugget, we talked about a few different file types that SQL Server has. We talked about the LDF file, which is the transaction log, or the T-log as we like to call it. And then the other file type I mentioned was MDF. And this isn't a great name, but you can think of this as the database file. Now, the fact is that contains more than just your data itself. This also contains your indexes, any triggers, any stored procedure code that gets created. Everything that has to do with the database lives in an MDF file. Now, there are certain instances, and we're going to talk in just a second about file placement strategies. There are certain instances where you do not want to put all of your eggs in one basket. And so the third file type you'll see is an NDF file, and that's just a secondary database file. So the database as a whole is all of these. You need the LDF to get your transaction log. You're going to have at least an MDF for all of the database stuff, and you might have one or more NDF files to spread the database stuff across multiple places. And again, we're going to talk about file placement strategies in just a second. So by default, a database will only have an LDF and an MDF. You have to decide if you want one or more NDF files. So when might you want to do that? Well, okay, file placement strategies. It's all about performance and reliability. Typically, you are going to want to put your LDF files on a separate disk from anything else. Ideally, you don't want them to be on the same disk as the operating system. You don't want them on the same disk as the SQL Server binary files, the program files for SQL Server. You definitely don't want them on the same disks as your databases. That way, as we discussed in the last nugget, if you have a crash of some kind, either a database file corruption or a disk goes bad or whatever else, your log files are separate from your database files. So that's step one, is to get those LDF files separate. Now, talking about operating system, typically in a really big environment, you'll see the operating system files on their own disk, and you'll see the SQL Server program files on their own disk. Mainly for performance reasons, because it's easier when you've got more platters contributing. Now, if you've got a really high performance, let's say a RAID array or something like that your operating system lives on, then it might be okay for you to put your SQL Server program files in the same spot. Just understand that, Windows is going to have to do a lot of reading from that disk, and as long as it's fast enough to keep up for both the operating system needs and for the SQL Server binaries, then you're fine. So that's kind of a back and forth, depends on your exact circumstances. Always have those LDFs on a separate disk though. All right, now let's talk about MDFs and NDF files. We're going to assume that we've created multiple NDF files for this example database that we're going to talk about. Okay, so first of all, where do you physically put these things? Well, again, it depends a little bit. Let's talk about the logical structure of the database for a second. Within a database, you've got multiple tables. So this is table 1, and this is table 2. You've also got things like indexes. We'll call this index 1, and we'll call this one index 2. When you create these things, you get to decide what file they're physically stored in. I can say table 1 is going to go in this file, table 2 is going to go in the same file. Index 1 is going to go into this file, and index 2 is going to go into that file. Well, what does this particular arrangement do for me? Well, keep in mind that a file at the operating system does have a certain amount of overhead. The more processes that are trying to read from a single file, kind of the more bottlenecky it can get. So if I were to take this MDF file and put it on disk 1, this NDF on disk 2, and this NDF on disk 2, well, what I've done there is I've brought more disks to play. I can have one disk worrying about getting the tables on and off of the physical disk and into memory. I can have another disk that's dealing with indexes. Now, because I've got these two indexes spread across two files, it'll be a little bit easier for separate processes to get in and pull information out of those two files simultaneously. They won't be competing for the same, sort of the same space on disk at the same time. They'll be working with different files. So one way to think about that is if you're familiar with Microsoft Access. It's really common for very small little workgroup type databases to get put into an Access file, and maybe you've got 5 or 6 people who are reading the same file from a network share. And that works fine until you start to get up to maybe a dozen, 15, 20 users, get up to 30, and then that access really starts to bog down because everybody's trying to jump in the same file at the same time. Similar, not exactly the same, but similar principle here. By spreading objects out across files, you can kind of reduce that resource contention. Now, here's the problem with spreading things out across files. If I back these things up, I want to back them up in such a way that I'm grabbing all the related data. Let's take a different look at this diagram. Let's say I've got a table that's storing orders, and another table that's storing items, and another table that's storing customers, and maybe I've got another table over here that isn't storing something that's so related to these three, because these three are very clearly connected to one another. Let's say I've got another table over here that's going to store employee bonus information. Now, bonuses are driven by orders, but there's not a direct day-to-day, minute-to-minute connection. It might be okay for me to take all of these and put them onto an MDF file, and to take this guy and put him onto an NDF file, because I could then back them up separately. If these files were truly huge, and I was having trouble getting backups of everything in a single day, dividing them up this way might make sense. Now obviously this MDF file is really critical, and I might want to back it up every night. This NDF file, well, maybe it's not as critical. Maybe that's data I could, if I needed to, reconstruct by going back over and looking at these orders. So maybe that file I'm only going to worry about backing up once a week. The trick with that is if, let's say I had orders in a separate file too. Let's say that only these two guys were in that MDF file and that this was in a separate NDF. Well, I would pretty much have to back both of those files up together. Now, SQL Server actually provides a way to do that. It's called a file group. So Here's one scenario you might look at. I might say that this MDF file is going to live on disk 1. This NDF file is going to live on disk 2, and that's going to help give me some better performance. That way, I've got two different disks contributing to the database. I don't have everything living in one place. However, because these are so tightly tied into one another, I need to back both of them up at the same time so that I have consistent data. So they're both going to belong to a single file group, and what I'll do is I'll back up that file group as a unit. Now, the reality of most production environments is that you're usually going to be storing your SQL Server databases on large RAID arrays. So you've already got multiple disks contributing to the situation. So you might not find yourself splitting tables and indexes across multiple files for performance reasons. You may, however, split them across multiple RAID arrays for performance reasons, or you may spread them across multiple RAID arrays for stability reasons, not putting all of your eggs in one basket. If one array has a massive problem of some kind, you don't lose all of your data all at once. Although keep in mind that related data will usually be in a file group, so that the connected tables can all be backed up and restored as a unit. And then you might have another file group for data that lives in the same database but isn't as tightly connected to those first set. So file placement strategies in SQL Server can get really, really detailed. In SQL Server 2008, there's actually another set of files you have to worry about. So we've already said you've got the LDF files, you've got your MDFs, and one or more NDFs, possibly. In SQL Server 2008, as we discussed in the last nugget, you've got this new thing called a file stream. And that's a way of storing large blocks of data outside of the database itself. Typically, so we're just going to call those file stream files. Now typically, these are going to want to live separate from the log. These are just files on an NTFS drive, and the database is pointing to them. So they do tie into the database's consistency. So they do need to be backed up with whatever portion of the database is pointing to them. So if I've got some tables on this MDF file that are pointing to those file stream files, then I need to make sure that they're all getting backed up together. It would not be very smart for me to restore this MDF and have it pointing to file stream files that weren't there because of a disk failure. So even though these are separate files, they're still part of the database. Even though they don't live inside the MDF file, you should think of them as living in the MDF file because the pointer to them does live in that file. There are all kinds of ways of allocating files and objects across files and across disks and so forth. None of them are perfect for every single situation. So what you're going to have to do is, in any given situation, look at what the goals are. Are the goals to spread things across multiple disks? Are the goals to improve backup time? Are the goals to improve reliability in case of a failure? All of those things contribute in. Just know that the basic deal is you want your logs, your LDFs, to be protected. You do not want your log files to have any opportunity to be wiped out at the same time as a database file. So you always want them to be separate, typically on a separate RAID array. Your MDF and NDF files are where your flexibility comes in. They allow you to spread database objects across multiple disks or across multiple arrays. So whatever goals you have, those MDF and NDF files are your way to do it. Your file stream files are really almost a liability. You have to make sure that they are connected in some way to whatever MDF and NDF files you've got going. You may choose to have your file stream files on a separate RAID array for performance reasons, but they need to be backed up and restored as a unit with whatever database they are sort of attached to. In this nugget, we looked at the physical architecture for SQL Server. We talked about how SQL Server supports multiple instances and how those instances compete for resource utilization on the server. We looked at the different services that each instance of SQL Server will run, and we talked about some of the best practices for running those under specific accounts and so forth. We talked about the database physical architecture, how each database can actually comprise of multiple different files, and how you can spread database objects across those files to achieve things like better performance, better redundancy, and so forth. I hope this has been informative for you, and I'd like to thank you for viewing.